In this lesson, we're going to talk about interpretations of the derivative. First off, we're going to create another notation for a derivative. Right now, we're using this f prime of x notation that we've been working with to think of the derivative as a function. But another way to think about the derivative is to remember that we had the average rate of change where we looked at it as delta y over delta x. Delta y over delta x was basically saying some change in y over some change in x, and that gave us our average rate of change. And then the way that we created the derivative is if we take this delta x and get it smaller and smaller and smaller, we called it the instantaneous rate of change. So the notation that we want to create is similar to delta y over delta x. We'll call it dy over dx. And think of that as some small change in y over some small change in x. When we look at it this way, we can remember that dy over dx is still some sort of ratio. Some sort of rise over run, it's just a rise over run at some infinitesimal scale. The downside of this notation is it doesn't really treat it like a function. So if we wanted to say f prime of c, basically take the derivative and plug in a value, we would have to write dy by dx evaluated at x equals c. A real mess. The reason I show you that is just in case it comes up in the homework. Let's do a couple of examples of how this is helpful. Let's suppose s is the position of an object at time t. We know that the position, or the distance if you will, if we take its derivative, it gives us the velocity. So now let's write this with the Leibniz notation. The Leibniz notation would write this as ds by dt, and that represents the derivative of the function that gives the position. This is the same as f prime of t. Now what kind of units are we looking at here? The units of s are distance units. The units of t are time units. And if you think about it, distance over time, that's exactly how we define velocity. Next example. If we have y equals f of x, we also know that the derivative f prime of x not only gives us instantaneous rate of change, but also gives us the slope of the graph, or we looked at it as the slope of the tangent line. Let's write this in Leibniz notation also. Dy by dx would be that Leibniz notation. Dy represents the rise, dx represents the run, so we have rise over run, which is exactly what we think of when we say slope. Now let's start doing some interpretations of derivatives. For the first example, let C be the cost in dollars of carpeting a house that is a square feet in area. We want to know the units and the interpretation of f prime of a. How would we interpret this derivative? Let's start off with the units by using the Leibniz notation. The Leibniz notation would be dc by dA, and remember C was the cost in dollars, and A was in square feet, so this is the dollars per square foot. That's a perfectly normal thing to talk about. So to interpret this, what would f prime of a actually represent? The way that we tend to do this is consider the next value. The next value, if you will. If I were to take the area and increase it by 1, the change in cost would be roughly equivalent to the derivative. And that's how we're going to interpret these things. Let's write that down more carefully. F prime of a represents the cost per square foot for the next square foot of carpet. Like I said, just the next is what we're looking at for each derivative. The next square foot of carpet when a square feet is already carpeted. So basically wherever we are, the derivative represents the cost, or whatever you're talking about, of the next item. Let's do another example that has some numbers in it. The cost of extracting t tons of ore from a copper mine is C equals f of t dollars. And now we're looking at f prime of 2,000 is equal to 100. Now I want to point out here, because of the nature of f of t, 2,000 is the tons of ore from the copper mine. And the 100 is what we really want to try to represent. Let's start off by considering the Leibniz notation again. dc by dt is in dollars per ton. So this derivative value of 100 is going to represent dollars per ton. And now if I bring it up the way that I talked about in the last example, what's really going on is that means the cost of the next ton of copper is going to cost $100. But the next one I can actually quantify this time. So the way that I'm going to write this is that the cost of the 2001st ton, the next one, of copper is $100. And that's the strategy in general. The next one is what the derivative value represents. It represents whatever quantity change, in this case the cost, of that very next item. This next example uses the strange Leibniz notation, again for the sake of exposing it to you in case it comes up in the homework. Q equals F of P gives the number of thousands of tons of zinc produced when the price is P dollars per ton. So this is a supply function, actually. When you have a price of P dollars per ton, this function is going to tell you how many thousands of tons the suppliers are willing to produce. And then we've got this weird notation. Let's start off by changing it to one that we're more familiar with. So our equivalent statement would actually be F prime of 900 is equal to 0.2, and the 900 is a price. This is a price in dollars per ton. Now the units of this are going to be a little bit strange, so let's just write it down. So we're looking at 1,000 tons out of dollars per ton. So basically what we need to think about is the next dollar per ton. Some sort of change in price is what we're looking at here. So I'm not going to call it the 901st dollar. Let's look at it as an actual change from $900 per ton to $901 per ton, because again, we're always thinking about next. If the price increases from $900 per ton to $901 per ton, that's the next part, zinc production will be increased by 200 tons. Now wait a second, where did I get 200 tons? Let me just point that out. Remember, our units were in thousands of tons. So 0.2 thousand would look much better if we change it to the number 200. For our next example, the time that a drug stays in a person's system is a function of the quantity administered in milligrams. We want to interpret a statement, which is actually just a function statement, and then interpret the derivative statement with units. So let's tell these two apart. F of 10 equals 6. 10 would be the quantity Q in milligrams, and 6 would be the length in hours. All we need to do is write a statement that matches up with those two variables together. That statement simply means that 10 milligrams of the drug will stay in the person's system for 6 hours. Now let's try to do the derivative statement. F prime of 10 equals 0.5 is again associated with Q equals 10. But remember, we're talking about next. So this is talking about the 11th milligram that we're thinking about, and that's going to give you a change in time due to that 11th milligram. So it means that the 11th milligram of the drug increases the time by 0.5 hours. And now let me mention one more thing. A question that's a great follow-up here is how long will 11 milligrams of the drug last? Based on what you see here, you can probably answer that question. It took 6 hours for the first 10 milligrams to be processed, and the 11th milligram will increase the time by 0.5 hours. So you might look at that and just say 6.5 is how long 11 milligrams would last. Let's take that a step further. What I just mentioned is what we call a tangent line approximation. Now if you want to read the technical side of what's going on, basically if we have a value of x that's close to a value that we know something about with a function value and its derivative, then we can use this formula to estimate the value of x so long as it's close to that a where we know some data. Now when I say close to, that can be a wide open approximation very dependent on the application. But nevertheless, if it is close, we would expect that it wouldn't be too far. Basically what this formula is doing is taking the function value that you know, plus this change value that you know, and multiplying by how far it's changing. In the last slide, I basically just said it only changed by 1, so delta x was 1, and I just added the two values together. Let's do a couple of other examples. Fertilizers can improve agricultural production. We all know that they definitely help. So corn production in this case will model by y equals f of x. X is the pounds of fertilizer used, and y is the value of the corn produced in that season. This is some really good fertilizer in this example. Just look at the numbers. But let's start off by interpreting the two statements. F of 5 equals 11,500. 5 pounds of fertilizer would give an $11,500 crop. Very good. Very good fertilizer. So then from that, let's talk about what the derivative would really mean. The derivative, again, would be referring to the next one. So when I say f prime of 5 is equal to a value, I'm really referring to the sixth one, the next one, if you will. So that sixth pound of fertilizer will raise the value of the corn by $350. Now let's use a tangent line approximation. If we want to estimate f of 6 and f of 10, what we're going to do is just add these things together, assuming that it keeps the same trend over time. For f of 6, this is as accurate as we can get because it's really just one mark away. But for f of 10, we'll talk a little bit further. The formula requires us to use data that we have. So the formula up here is f of a plus f prime of a times delta x. I'll explain each of those as we go, but we're starting with f of 5 and f prime of 5. Now, the value of delta x is actually going to be the difference between where we were and where we're going. We were at 5 and we're going to 6, so that is 1 away from where we started. Then we'll put in the values. F of 5 was 11,500. F prime of 5 was 350, and I won't bother to write the times 1. If we add that together, we get $11,850. That's how much we would expect the corn to be worth after 6 pounds of fertilizer. Now let's do it for 10. For 10, we're looking at the same thing with f of 5 plus f prime of 5 because that's the data that we have. But for delta x is how far we are from what we were given to where we're going. And the difference between 5 and 10 is 5. Now let's put our numbers in again. If I put these values in, I get $13,250. That's the value of the corn that we're estimating if we use 10 pounds of fertilizer. Now here's the problem. 10 is double the amount of fertilizer. It's very far from the data that we have, so I wouldn't necessarily expect 10 to be very valid, but 6 is pretty good. 6 is more accurate because it's closer to the data.